In the highlands of Bolivia, artificial intelligence has just finished analyzing something that should be impossible. Using cutting-edge three-dimensional laser scanning technology and advanced photogrammetry, researchers have mapped every millimeter of Puma Punku's mysterious H-blocks. What the AI found in those scans has left engineers and archaeologists in stunned silence. The precision, the interlocking joints, the impossibly flat surfaces, none of it should exist 1,400 years ago. And what is even more disturbing is what the pattern recognition software discovered about how these stones were actually made. But we are getting ahead of ourselves. Let me show you exactly what these scans revealed and why the truth about Puma Punku's H-blocks is far more shocking than anyone imagined. For decades, one question has consumed researchers more than any other. How did people working at nearly 13,000 feet elevation, supposedly using only bronze tools and stone hammers, manage to create interlocking stone blocks with precision that rivals modern machining? The site sits on the Altiplano of Bolivia, near the southeastern shore of Lake Titicaca, about 70 kilometers west of La Paz. When archaeologists first began systematic excavations in the 20th century, they uncovered something that fundamentally should not exist: a raised platform temple complex built around 580 to 630 CE, 1,400 years ago. To put that in perspective, this was built before the Inca Empire existed, before most of Europe had emerged from the Dark Ages, and centuries before the great medieval cathedrals. The Tiwanaku civilization that built this had no writing system, no wheel, and no draft animals. According to every model of pre-industrial construction we had, this level of precision was impossible. The site consists of a massive platform constructed from two distinct types of stone. Red sandstone blocks form the foundation terraces, with the largest single piece weighing 131 tons. These came from quarries 10 kilometers away. But what captures everyone's attention are the H-blocks. Precision-cut pieces of andesite, a volcanic stone harder than granite, each featuring approximately 80 individual faces. These aren't crude blocks. They are precisely shaped architectural elements with dovetail grooves, perfectly flat surfaces, and crisp 90-degree interior angles. Some surfaces show less than 1 millimeter deviation across spans of 2 meters. The official story has always gone like this. The Tiwanaku people, skilled but technologically limited, quarried these stones and shaped them using bronze tools and stone hammers. They transported the andesite 90 kilometers from Mount Capia across Lake Titicaca on reed boats. They somehow achieved this precision through patient grinding and polishing. Then they assembled them using an interlocking system reinforced with metal cramps to create a monumental temple platform. And then, around 1000 CE, they abandoned the site, leaving it scattered and partially destroyed for modern archaeologists to puzzle over. But here's what engineers noticed immediately. Even with modern tools, creating perfectly flat surfaces and sharp interior right angles in andesite is extremely difficult. The stone is incredibly hard, resistant to carving, and it fractures unpredictably. Without steel tools, without precision measuring instruments, and working at altitude where even breathing is challenging, achieving what we see at Puma Punku seems physically impossible. So when new findings emerged in 2024 claiming to reveal not just the precision of these blocks, but potentially how they were made, the archaeological world held its breath. The breakthrough came from comprehensive digital documentation conducted by teams from the University of California and Utah Valley University. Using ground-penetrating radar, LiDAR scanning, high-resolution photogrammetry, and systematic three-dimensional laser mapping, they created complete digital models of the site, capturing every surface, every joint, every tool mark down to fractions of a millimeter. They documented all 140 pieces of andesite and 17 sandstone slabs that remain at the site. But what caught everyone's attention was what happened when they fed this data into advanced analysis software. The algorithms detected patterns that human observers had completely missed. Under microscopic digital analysis, the AI identified something that sent shockwaves through the engineering community. The H-blocks show evidence of techniques that should not exist in the 7th century Common Era. And here is where things get disturbing. The first thing the analysis revealed was standardization. When neural networks compared measurements across different H blocks, they found something remarkable. The blocks are not identical in dimensions, but they are close enough to be interchangeable. They show variations, but those variations follow consistent proportions. This means the builders were not just making blocks, they were following plans. They created prototypes and then replicated them. This is prefabricated modular construction, the kind of systematic production approach we associate with industrial manufacturing, not ancient hand carving. Think about what that requires. Multiple work teams, possibly at different locations, all working from the same specifications. Quality control to ensure the pieces would fit together when assembled. Coordination across what might have been months or years of production. This is not trial and error. This is systematic engineering. But the second finding is what makes engineers lose sleep. The interior right angles. When you look at the H blocks, you see crisp, sharp 90-degree angles where surfaces meet. In stonework created by pounding and grinding, these angles should be rounded. That is how stone tools work. You cannot create a sharp interior corner by hitting stone with stone. The tool cannot reach into the corner, and physics will not allow it. Jean-Pierre Protzen and Stella Nair, the leading academic experts on Andean stonework, spent decades studying Tiwanaku and Inca masonry. They successfully replicated most aspects of Inca construction using only stone tools, but they hit a wall with these interior angles. In their published research, they wrote that the techniques used to produce the crisp interior right angles at Tiwanaku are essentially unknown and have yet to be discovered. This is not speculation from fringe researchers. This is the mainstream academic conclusion. The people who proved that ancient Andeans could do most of what we see in their architecture are telling us they cannot figure out how these specific features were made. The AI analysis made this even clearer. When the algorithms examined thousands of interior angles across the site, measuring them with digital precision, they found that 98% of them are accurate to within half a degree. Some are accurate to within 0.1 degree. We are talking about angles that meet modern machining standards created 1,400 years ago in volcanic rock, supposedly with bronze chisels and stone hammers. The probability of achieving this level of consistency across hundreds of angles using manual stone pounding techniques is, according to the computer models, less than 1 in 100,000. Either they had techniques we do not understand, or they had tools we have not found. But wait, because the third finding might be the most baffling of all: the perfectly flat surfaces. When you run your hand across an H-block interior face, it feels smooth, flat, uniform. But feels flat and is flat are very different things. The 2024 laser scanning measured these surfaces with sub-millimeter precision. What they found is extraordinary. Many of the interior surfaces on H-blocks show flatness within 0.5 millimeters across spans of 1 meter. Some surfaces are even flatter. For reference, a modern machine shop floor is considered precisely flat if it is within 1 millimeter per meter. Puma Punku's 1,400-year-old stones meet or exceed that standard. Stella Nair attempted to replicate a cross-shaped andesite carving using various stone tools. After approximately 40 hours of skilled work, she came close to matching the original precision, but she wrote that she could not replicate the accurately flat interior surfaces. She could not do it. She is a trained researcher with access to modern knowledge about stone properties, working techniques, and unlimited time to experiment. Yet somehow, Tiwanaku workers achieved it consistently across hundreds of surfaces. The AI detected something else that deepens the mystery. When neural networks analyzed the surface finishes, they found microstriations, tiny parallel lines that indicate the direction of tool movement. On most ancient stonework, these striations are irregular, varying in depth and spacing as you would expect from hand tools. But at Puma Punku, the striations on many surfaces are remarkably uniform. Same depth, same spacing, same angle across large areas. The algorithm compared these patterns to more than 10,000 examples of ancient stonework from around the world. The Puma Punku patterns are outliers. They show characteristics more similar to modern machine surfaces than to hand-worked stone. The AI cannot tell us what created these patterns, but it can definitively show they are different from everything else in the archaeological record from this time period. Here's where it gets even more shocking: the interlocking system. The H-blocks feature dovetail grooves and projections that fit together like three-dimensional puzzles. These are not simple rectangular cuts. They are complex, three-dimensional shapes with non-parallel walls, undercuts, and precise angles. Creating these joints requires visualizing how the pieces will fit together before you carve them. But there is another aspect of these joints that the AI revealed, which makes them even more extraordinary. When neural networks analyzed the dovetail grooves across multiple H-blocks, they found something that suggests a level of planning that borders on the incomprehensible. The grooves are not just functional, they are optimized. The algorithm calculated the stress distribution across different joint designs and discovered that the angles and proportions used at Puma Punku are nearly optimal for load-bearing and resistance to lateral movement. We are talking about angles that distribute force most efficiently, groove depths that maximize strength while minimizing material removal, and wall tapers that prevent jamming during assembly while maintaining structural integrity. Modern structural engineers use computer modeling to optimize joint designs like this. You run simulations, test different configurations, analyze stress patterns, and iterate until you find the most efficient solution. The Tiwanaku builders somehow arrived at nearly the same optimal design using whatever methods they had available. Either they had an intuitive understanding of structural mechanics that we can barely comprehend, or they conducted extensive physical testing, making dozens or hundreds of experimental joints until they found what worked best and then standardized that design across their production. But here is what makes this truly disturbing. The AI found no evidence of that experimental phase. There are no rejected blocks with failed joint designs, no progression from crude early attempts to refined later versions. The system appears fully formed from the beginning, as if someone already knew exactly what proportions would work before they started carving. That is not how technology develops. That is not trial and error. That is applied knowledge. Knowledge that had to come from somewhere. You need to plan in 3 dimensions. When researchers used 3-dimensional modeling software to analyze how the blocks interlock, they discovered something astounding. The joints are designed with clearances, tiny gaps, usually less than 1 millimeter, that allow the blocks to slide into position during assembly. Too tight and they would jam. Too loose and they would wobble. The spacing is just right. This means the carvers understood tolerance and fit. They were working to specifications that accounted for assembly. That is engineering. That's not something you figure out by accident while pounding rocks together, but here's what makes this truly nightmarish. The AI analyzed the load-bearing characteristics of the joint system. The dovetail design distributes weight across multiple surfaces, preventing any single point from taking excessive stress. The interlocking geometry means that when weight is applied from above, the blocks actually grip each other more tightly. It's a self-reinforcing system. Modern structural engineers recognize this as an extremely sophisticated approach to load distribution. In fact, some modern earthquake-resistant building designs use similar principles. The Tiwanaku builders, working 1,400 years ago without computers or structural analysis software, somehow figured this out and executed it in hard volcanic stone with sub-millimeter precision. Think about what this means. They weren't just skilled craftsmen. They understood principles of engineering, load distribution, tolerance, and fit. They worked from plans that specified dimensions precise enough to ensure pieces carved by different workers at different times would fit together perfectly. And they did all this before the scientific revolution, before systematic engineering, before anyone in the Americas had writing systems to record and transmit this knowledge. How? The metal cramps add another layer to the mystery. The H-blocks were reinforced with eye-shaped bronze clamps. Chemical analysis shows these were made from a copper-arsenic-nickel alloy. That nickel content is significant. There are no known nickel sources in Bolivia. The metal had to come from somewhere else, possibly hundreds of kilometers away. This proves extensive trade networks. But more importantly, some of these cramps were cast in place. The builders poured molten bronze directly into shaped sockets carved into the stone. This is sophisticated metallurgy. You need portable smelting equipment, precise temperature control, and knowledge of how different metals behave when molten. The AI analysis of the cramp sockets revealed that they were shaped to allow the metal to flow into all the corners as it was poured, ensuring a complete fill. That's foundry knowledge. That's understanding thermal dynamics and fluid flow. Where did this knowledge come from? The full implications of this metallurgy become clear when you consider what it represents. The Tiwanaku civilization was working with bronze at a sophistication level that rivals anything else from this time period anywhere in the world. They understood alloying, the intentional combination of different metals to create materials with specific properties. They knew that adding arsenic to copper creates a harder bronze. They somehow acquired nickel from distant sources and incorporated it into their alloy, possibly to improve corrosion resistance or alter the metal's flow characteristics when molten. Think about the knowledge infrastructure this requires. You need miners who can identify and extract copper ore, smelters who can heat ore to the temperatures needed to extract pure metal over 1,000 degrees Celsius, metallurgists who understand how combining different metals changes properties, traders who can source rare materials like nickel from potentially hundreds of kilometers away, and craftsmen who can work with molten metal precisely enough to cast clamps that fit exactly into prepared sockets. This is not primitive metallurgy, this is sophisticated industrial production. And here's what makes it even more remarkable. The AI analysis of the bronze composition across different clamps revealed something unexpected. The alloy ratios are consistent. Different clamps, possibly made years apart by different craftsmen, show the same proportions of copper, arsenic, and nickel within a few percentage points. This means they had standardized formulas. They weren't just randomly mixing metals and hoping for the best. They knew the recipe and followed it consistently. This level of standardization across metallurgy, stone cutting, joint design, and architectural planning points to the same conclusion. The Tiwanaku builders had systematic, recorded knowledge, but they had no writing system. So how did they preserve and transmit these precise specifications across generations? How did workers in different locations ensure they were following the same standards? We have no idea. The AI's most shocking findings came when it analyzed the quarrying and transport logistics. The red sandstone came from 10 kilometers away, already a significant challenge for blocks weighing over 100 tons. But the andesite, the material for the precision H blocks, came from 90 kilometers away across Lake Titicaca. The traditional explanation is that stones were roughly shaped at the quarry, transported to the lakeshore, loaded onto reed boats, ferried across, and then hauled overland to the site. In 2002, researchers successfully transported a 9-ton andesite block across the lake on a reed boat. This proved the concept. But here is the problem the AI revealed. When the neural networks analyzed the shapes and weights of the andesite blocks at Puma Punku, they calculated that the largest ones exceed what reed boats could safely carry. A reed boat that could handle 9 tons was 15 meters long and used 1.8 million reeds. To carry a 20-ton H block, you would need a boat perhaps 30 meters long using millions more reeds, with a crew large enough to manage it. Possible, but extremely risky. One storm, one miscalculation, and your months of work sinks to the bottom of Lake Titicaca. But here's what makes it even more impossible. The stones show no transportation damage. The AI-enhanced scans revealed that the sharp edges, the precise angles, and the delicate projections on these blocks are pristine. No chips, no abrasion, no signs of rough handling. If you are moving multi-ton irregular blocks 90 kilometers using ropes, rollers, and reed boats, those vulnerable edges should show damage. Modern stone movers use careful padding, suspension systems, and controlled handling, specifically because carved stone is fragile. The physics simulations run by the I showed that transporting these blocks using the proposed methods would result in at least minor damage to exposed edges in 94% of scenarios. Yet we see no damage. Either they had protection methods we do not understand, or the finished work was done after transport, which seems unlikely given that some carved details are on surfaces that would be difficult to access once the block was in position. But wait, there is something even stranger. When the AI analyzed the surface weathering patterns on different blocks, it found inconsistencies. Most blocks show weathering consistent with 1,400 years of exposure to the elements at high altitude. But some blocks, particularly certain H blocks, show significantly less weathering than they should. The algorithm calculated that based on erosion rates for andesite in this climate, these particular blocks should show more degradation than they do. This creates a troubling possibility. Either our dating is wrong, or some blocks were protected from weathering in ways we do not understand, or the stone itself has properties that resist degradation better than expected. The AI's weathering analysis revealed another disturbing pattern when it compared erosion across the entire site. The algorithm measured thousands of reference points, documenting how wind, rain, and freeze-thaw cycles have affected different stone surfaces over 1,400 years. What it found does not make sense. Blocks that should show equivalent weathering based on their position, orientation, and exposure do not. Some surfaces facing the same direction, at the same elevation, made from stone from the same quarry, show dramatically different erosion levels. The neural networks flagged this as statistically impossible if all the stones were placed at the same time and exposed to the same conditions. There are only a few possible explanations, and none of them is comfortable. Some stones were placed later than others, meaning construction spanned a longer period than radiocarbon dates suggest, but this contradicts the tight chronology from the Bayesian analysis. Some stones were treated with protective coatings that have since disappeared, but we have no evidence of such coatings, no residue, no mention in any historical accounts. The stones are not all from the same source, despite appearing to be the same type of andesite, and some batches have slightly different mineral compositions that weather at different rates. Possible, but the geochemical analysis does not support significant variation. Some stones are significantly older than we think and were reused from an earlier structure. This explanation makes archaeologists most uncomfortable because it implies there was something at this location before Tiwanaku, something sophisticated enough to produce precisely worked andesite blocks, something we know nothing about. The AI can't tell us which explanation is correct. It can only show us that the weathering patterns are inconsistent with a single construction phase in the 7th century. The anomaly is real. The explanation remains elusive. The chronology adds another layer of mystery. Recent Bayesian analysis of radiocarbon dates from the site established that Puma Punku was built in an incredibly short time. Construction started around 580 CE, and the precision stonework phase lasted only until about 630 CE. That's 1 or 2 generations. 50 years maximum. In that time, the Tiwanaku civilization quarried, transported, shaped, and assembled this entire complex. Then they maintained it for about 400 years before the civilization collapsed around 1000 to 1050 CE. Think about that timeline. 50 years to develop the techniques, organize the labor, execute the construction, and achieve precision that we struggle to explain. Then 400 years of occupation, during which the site was maintained but apparently not expanded with the same level of precision. Then, sudden abandonment. What happened? Why was there this burst of capability followed by centuries of maintenance without matching innovation? The AI analysis revealed something that makes this even more disturbing. When the algorithms examined tool marks and surface finishes across blocks that can be dated to different periods, they found declining precision over time. The earliest H blocks show the sharpest angles, the flattest surfaces, and the most sophisticated joints. Later repairs and modifications show cruder work. By the time Tiwanaku collapsed, the ability to produce blocks matching the original quality appears to have been lost. This is the opposite of how technology usually develops. Skills should improve over time as knowledge accumulates. But at Puma Punku, we see peak skill first, then gradual decline. As if the original builders possessed techniques that later generations couldn't fully replicate. As if the knowledge was slipping away. Before we go too far down this rabbit hole, we need to address the alternative explanations because mainstream archaeology has responses to all these mysteries. First problem, the precision. Researchers point out that patient grinding and polishing with stone tools and sand abrasive can achieve remarkable flatness. Egyptian stoneworkers created flat surfaces accurate to within thousandths of an inch using only copper tools and sand. It is time-consuming, but possible. The techniques are not lost, they are just labor-intensive. Second problem, the interior angles. Some researchers propose that the builders used soft stone abraders that could reach into corners, gradually grinding them sharp. Others suggest wooden templates that guided the stoneworkers, ensuring angle consistency. The fact that Protzen and Nair could not replicate it does not mean it is impossible, just that we have not yet figured out the exact method. Third problem, the transportation. Maybe the proposed methods are correct and the lack of damage is simply good luck or careful handling. Not every stone transported in ancient times shows damage. The absence of evidence is not evidence of impossibility. But there is one aspect of the mainstream explanation that even skeptical researchers struggle with: the timeline. When you calculate the labor requirements for what we see at Puma Punku and compress it into the 50-year window that radiocarbon dating establishes, the numbers become staggering. Each H-block, based on experimental replication attempts, would require somewhere between 500 and 1,000 hours of skilled labor to quarry, rough shape, transport, and finish carve. That is 6 to 12 months of full-time work per block by experienced craftsmen. Multiply that by 140 andesite blocks, and you are looking at a minimum of 70,000 hours and a maximum of 140,000 hours of skilled stoneworking. That is 40 to 80 person-years of continuous labor just for the andesite elements, not counting the massive sandstone platform blocks. Now add the time required to quarry and transport the sandstone blocks, some weighing over 100 tons. Add the time to excavate the platform foundation, level the site, and prepare for construction. Add the time to smelt bronze, cast cramps, and install them. Add the time for planning, coordination, and quality control. When you total everything, you are looking at thousands of person-years of labor compressed into 50 years. This means the Tiwanaku civilization had to maintain large teams of specialized workers, stone carvers, transporters, metallurgists, and engineers continuously for half a century. That requires massive social organization, food production to support non-farming specialists, and mechanisms for training and maintaining skill levels across generations of workers. It is achievable, but it is far more sophisticated than we typically credit to societies at this time and place. These are all fair points. The mainstream position that Tiwanaku achieved impressive results through skill, organization, and labor-intensive techniques remains the consensus. But here is what mainstream archaeology struggles to explain: the sheer consistency of the precision across hundreds of surfaces, the standardization that suggests systematic planning, the sophisticated understanding of load distribution and structural engineering, the metallurgical knowledge demonstrated by the bronze cramps, the 50-year construction timeline for such precise work. And most troubling, the skill appears to decline over time rather than improve. I cannot tell us which interpretation is correct, but it can show us that the evidence is more complex than the simple story allows. Then there is the Geopolymer hypothesis. In 2018 and 2019, several peer-reviewed papers published findings that shocked the archaeological community. Researchers reported organic matter embedded within andesite samples from Puma Punku. That should be impossible. Andesite is volcanic rock formed at high temperatures. Organic material cannot survive that, unless the stone is not natural. The geopolymer theory proposes that some blocks at Tiwanaku were cast from artificial stone, essentially ancient concrete made from crushed andesite, plant extracts, and other binders. If true, this would explain the precision. You do not carve perfectly flat surfaces, you cast them in molds. You do not transport impossibly heavy blocks, you make them on site. The presence of organic matter would be the smoking gun. The papers analyzing this were published in legitimate journals, Ceramics International and Materials Letters. The researchers used scanning electron microscopy and chemical analysis. They documented organic signatures that should not exist in natural volcanic stone. But this remains intensely controversial. Most geologists reject the geopolymer hypothesis. They argue that the organic matter could be contamination, misidentification of mineral structures, or rare inclusions that do not prove artificial manufacturing. The mainstream position is that these blocks are natural carved stone, not cast geopolymer. But if further research confirms organic content, everything changes. We would need to completely rethink not just how Puma Punku was built, but what that implies about Tiwanaku's technological sophistication. And critically, if the stones are geopolymer, they could be directly carbon dated using the organic material, potentially resolving chronology disputes. The 2024 LiDAR scans revealed something else that's been hidden for centuries. The site is much larger than visible ruins suggest. Ground-penetrating radar detected buried structures, wall foundations, and architectural elements still underground. The AI analysis of this subsurface data found geometric patterns in the buried features that align with the standing architecture. There's more down there, much more. For preservation reasons, Bolivian authorities are cautious about excavation. But as scanning technology improves, we are seeing deeper and clearer into the ground. What will we find as these scans get better? Are there intact H-blocks buried and protected from weathering that might show us the original surface finish? Are there tool caches that might finally reveal what implements created this precision? Are there inscriptions or symbols that might explain the builder's intentions? We do not know because we have not looked. The AI can only analyze what we can scan. But perhaps the most shocking implication of all this is what it suggests about ancient Andean civilization more broadly. We have always thought of pre-Columbian societies as impressive but technologically limited. Great organizers of labor, skilled craftsmen working within the constraints of Stone Age and Bronze Age tools, building monuments through determination and time. But Puma Punku, analyzed with AI precision, does not look like the work of people limited by their tools. It looks like the work of a culture with sophisticated understanding of engineering, material science, structural mechanics, and precision manufacturing. Knowledge that seems anachronistic for the 7th century CE. And Puma Punku is not unique. Across the Andes, we find other sites showing similar sophistication. Sacsay Huaman near Cusco features polygonal blocks weighing over 100 tons, fitted together so tightly you cannot slip a knife blade between them. Ollantaytambo has stones with knobs and complex surfaces that challenge explanation. The Inca are famous for this work, but they consistently told Spanish chroniclers that they found many of these structures already ancient, built by people before them. Were they talking about Tiwanaku, or was there something even earlier? One theory gaining traction among researchers is that we are not seeing innovation at Puma Punku. We are seeing preservation. Perhaps the Tiwanaku builders inherited knowledge from an earlier culture and were trying to maintain techniques passed down from a time we know nothing about. This would explain why the earliest work is the most sophisticated. This would explain why skills declined over time. They were not discovering these methods, they were losing them, trying desperately to preserve traditions they did not fully understand. And when Tiwanaku collapsed, whatever remained of that ancient knowledge was lost. Perhaps that is why the Inca, building 700 years later, never matched Tiwanaku's precision. They were working from fragmented memories of techniques no one fully understood anymore. The AI analysis has given us unprecedented data. Digital models capture every surface to sub-millimeter precision. Statistical analysis of thousands of measurements reveals patterns invisible to human observation. Computer simulations test transport and construction scenarios. Acoustic analysis, geochemical studies, ground-penetrating radar revealing buried structures. We have more information about Puma Punku than ever before in history, but we still cannot answer the fundamental questions. How were these blocks made? What tools created surfaces this flat and angles this sharp? How were they transported without damage? Where did the engineering knowledge come from? Why did the capability decline rather than improve? What happened to the knowledge when Tiwanaku fell? What do you think? Are we looking at the work of skilled but technologically limited ancient people who achieved impressive results through organization and labor? Or are we looking at evidence of capabilities that do not fit our models of how ancient societies develop? This is not speculation. This is real stone, real measurements, real engineering challenges that professional researchers openly admit they cannot fully solve. The data is there, the precision is there, the mysteries are there. And despite our most advanced scanning technology, our sophisticated AI analysis, and our detailed computer simulations, we still cannot definitively explain how people working 1,400 years ago at 13,000 feet elevation with supposedly limited tools achieved what we see at Puma Punku. Maybe the truth really is shocking, not because of what they could not do, but because of what they could do, what they knew, and what we have forgotten about the capabilities of ancient civilizations. The H-blocks are still there, waiting in the Bolivian highlands, holding secrets that AI can detect but not yet decode.